Welcome, my dear students, on a new lecture of functional analysis. In the previous lecture, we had discussed about the fundamental properties of linear operators which have been defined on a vector space. From this lecture onwards, we will be discussing about a special class of linear operators called bounded linear operators. So the main reason behind studying these bounded linear operators is the fact that it characterizes the operators in general, or in other words, it helps us to characterize some class of operators with a specific property. The special case is the continuous. There are operators which are continuous. There are linear operators which are continuous. So, boundedness can be used to characterize such operators. So this is one of the main reasons behind studying bounded linear operators in general. There are many other properties of bounded linear operators as well. So we will be discussing about bounded linear operators. So this section mainly deals with bounded linear operators. Okay, so without further ado, let us define what is actually a bounded linear operator. So definition is, let x and y be normed spaces. Let capital X and Y be normed spaces. T from dt to y be a linear operator where dt is a subset of d of t is a subset of capital X. The operator t is said to be bounded. The operator t is said to be bounded if there exists a real number c such that for all x belongs to d of t means the domain of t, norm of t of x should be less than or equal to c into norm x. Okay, so if you are given with the two normed spaces x and y, a linear operator from the domain x, which is where domain d of t, which is a subset of x, onto y, is said to be a bounded linear operator if it satisfies the linearity condition, and the second property is that there exists a constant c, real number c, such that for any x belongs to the domain, norm of tx should be less than or equal to c into norm x. Please understand that this norm, the first norm of tx is an element in capital Y. So norm of tx, or the norm which is defined with respect to tx, is the norm in capital Y, and x is an element in d of t, which is a subset of capital X. So here the norm is actually with respect to the norm in capital X. So we have two normed spaces x and y. It may have two different norms. T of x is an element in capital Y. So norm of T of x means here the norm is defined with respect to the norm in capital Y. X is an element in capital X. So norm with respect to this should be a norm which is defined in capital X. So the thing which we have to understand is the fact that both of this norm need not be the same. Okay, so we do not represent it as norm 1, norm 2. We generally represent it as norm of Tx less than or equal to norm C into norm x. You should be able to understand that these two norms are norms defined on the spaces y and x respectively. It is somewhat different from the functions which we call a bounded function. A function is said to be bounded if the range is actually a bounded set. That's the boundedness in functions means. But in the case of linear operators defined on normed spaces, the boundedness actually means it maps bounded set onto the bounded set. That's the only meaning here. It does not mean that the range set is actually a bounded set. It does not give an idea about the range set is bounded or not. Okay, so you have to please understand that the function, real valued function, in the case of real valued function, boundedness, that concept is not exactly similar to the boundedness of linear operators defined on normed spaces. So that's the thing. Let's move on to further properties of normed bounded linear operators. So if T is a bounded linear operator, if T is a bounded linear operator, then T satisfies this condition. Then norm of Tx should be less than or equal to C into norm x. This should hold for every x element of the domain. If x is equal to 0, then Tx should always be equal to 0. So this inequality holds for every C in the case when x is equal to 0. So if you avoid that, because when x is equal to 0, this inequality is actually trivial. We get that. This holds for every C because the domain and range is actually 0. So if x is not equal to 0, the validity of this inequality implies that the space is the operator is actually bounded. Okay, we can actually exclude the case when x is equal to 0, which is trivial. Now, so this means this implies this inequality implies norm of Tx by norm of x less than or equal to C. Okay, this is actually possible when, since we have considered that x is not equal to 0. If in x is not equal to 0, norm x cannot be equal to 0. When T is bounded, this inequality should be holding. That is, norm of Tx divided by norm x should be less than or equal to C for some C. If it satisfies for some C, it should be satisfied for every real number which is greater than C. If it is satisfied for, let's say, C is equal to 2, it should be satisfying for C is equal to 3, 4, 5, 6, 7, etc. Okay, so if T is bounded, this inequality holds for a particular C implies that this inequality holds for infinitely many C's. So we do not need to find a C which is larger than a particular number. We do not need to find a C with which this condition holds and the C is a very large number. What our objective is actually to find a C such that this inequality holds for the least C. Okay, so such a C is called actually the norm of the operator. So the norm of the operator T, the norm of the operator, norm of the operator T, which is denoted as norm T, should be equal to the least value of C such that this thing holds, or in other words, C is actually the upper bound of this collection. If you take the collection norm of Tx divided by norm x for all x belongs to x not equal to 0 and x belongs to d of t, C is actually an upper bound of this collection. And we want the least C. So we want the least among the set of all upper bounds of this collection. Okay. So the least among the set of all upper bounds is actually the supremum. So norm of t should be defined as the supremum of set of all x belongs to d of t such that x not equal to 0, such that norm of t of x divided by norm x. Okay, which means that whenever t is bounded, this inequality holds for a particular c. Then it holds for every real number which is greater than c. We want the least real number with which this inequality holds. Such the least number with which this inequality holds is called the norm of the operator. Or in other words, if you consider these numbers, this collection norm tx by norm x, this real number c is called an upper bound of this collection. This is holds for every x not equal to 0. Now we want the least among the set of all upper bounds. The least among the set of all upper bounds is actually the supremum. So norm t can be defined as the supremum of set of all x belongs to the domain x not equal to 0 such that norm tx divided by norm x. So which is called the norm of the operator. And also this is defined in the case of the domain consisting of elements other than 0. If the domain consisting of only the 0 elements, we do not use this definition. We consider our norm t to be 0, or norm of the operator to be 0. So this holds whenever t is bounded. Now instead of c, we can actually substitute norm t, because this norm t is actually the least among the set of all c in which this inequality holds. Okay, so norm t is a particular value of c with which this inequality holds. So if t is bounded, we can write it as norm tx by norm x should be less than or equal to norm t, which implies norm tx should be less than or equal to norm t into norm x. So in the case of a bounded linear operator, we can define the norm of the operator as well. Using the bounded linear operator, the definition, we have defined the norm of the operator. Now let's move on to characterizing this norm of the operator, or identifying the properties of this norm of the operator. So next objective is to finding what are the basic properties of this norm. The other properties of the norm can be represented as a lemma. So the lemma states that let T be a bounded linear operator. Let T be a bounded linear operator, okay, which we have defined. Then condition 1, an alternate formula for the norm of T is actually for norm of T is norm T is equal to supremum x element of d of t norm x equal to 1 norm of tx. This is the alternate definition of the norm. Instead of x not equal to 0, we consider only those x whose norm is actually 1 and the image of those elements and take in the supremum. And the second condition is the norm satisfies all the properties of a norm. the properties n1 to n4, which we have used to define what is actually a normed space. So if T is a bounded linear operator, then we can use another definition to define norm of an operator, which is defined as supremum of x element of domain with such that norm x is equal to 1 with the norm Tx. Instead of norm Tx by norm x, we consider those elements whose norm is 1 and the image of the norm of those elements and taking the supremum. The second thing is this norm T. Here this norm means norm T satisfies all the properties of the normed space. Okay, so properties n1 to n4. Let's prove this theorem. Proof. Let's consider any x which is not equal to 0 with norm x equal to some real number a. Associated with this, define a new element y is equal to 1 by a times x. Okay, where x is not equal to 0, since we consider since x is not equal to 0, we can consider that y should not be equal to 0, and norm y should be equal to norm of 1 by a x. Okay, so which is equal to, which can be written as norm x by a. If you take the 1 by a outside using the properties of norm, and a is norm x, so we do not actually have to substitute mod a in that, because norm x is equal to a, which means a is always positive. So instead of a, we substitute norm x, which is equal to norm x by norm x, which is equal to 1. So if you take an arbitrary element x which is not equal to 0 in the domain with norm x is equal to a, associated with that we can define another element y is equal to 1 by a x which is not equal to 0, such that norm y is equal to 1. Now let's move on to the definition. So norm t is equal to, by the definition, supremum x element of d of t and x not equal to 0, norm Tx by norm x. Here we have 1 by norm x, which can be written as 1 by a. So which is equal to supremum x element of d of t, x not equal to 0, 1 by a into norm Tx. Now by the properties of linearity of t, we can include this 1 by a onto the inside of the norm. Okay, by the basic properties of norm, so we can write it as, which is equal to supremum x element of d of t, x not equal to 0, norm of 1 by a into Tx. Since t is linear, we can substitute this 1 by a onto the inside of t. So this is equal to supremum x element of d of t and x not equal to 0, norm of t of x by a. We have already defined that x by a is actually y. 1 by a x is actually y. So this is equal to supremum x element of d of t, x not equal to 0, norm of ty. Here we do not have any y. We have to take the supremum over x, but here the element is defined with respect to y, so we have to consider, or we have to change this in terms of y as well. So y has the property that y is an element of d of t and y not equal to 0, and the third property is norm y is 1. So we can write it as supremum y element of d of t, norm y equal to 1, norm of ty. So norm t can be written as supremum y element of d of t, norm y is equal to 1, norm of ty. So instead of y, if we replace y by x, because this definition is independent of its variable, supreme of x element of d of t, norm x is equal to 1, norm t of y is equal to norm t, this which is what we have to prove. So the first part is proved. Now moving on to the second part. In the second part, we have to prove that it satisfies all the properties n1 to n4 of a norm. So norm t from the previous definition is defined as supremum x element of d of t, norm x is equal to 1, norm of tx, which is the definition which we have proved. Here, since norm of tx is always greater than or equal to 0, okay, because it is a basic property of norm, and this means that supreme of the quantities which is greater than or equal to 0. Supreme of every set which is greater than or equal to 0 is always greater than or equal to 0. From this we can imply that norm t is actually greater than or equal to 0, which is n1, because norm tx is greater than or equal to 0. By the property of norm, supreme of the collection of elements which is greater than or equal to 0 is always greater than or equal to 0 by the property of supremum. Now the second property is norm t equal to 0 implies supremum x element of d of t, norm x is equal to 1, norm of tx is equal to 0. Supreme of this quantity is equal to 0, each of this quantity should be equal to 0. So because supreme is the upper bound, actually upper bound is equal to 0, and each of this actually a positive quantity, which means that actually t of x is equal to 0 for all x, or in other words tx is equal to 0 for all x. Here instead you can substitute, instead of this definition you can substitute the other definition as well. Using the other definition, x not equal to 0, here we can substitute by norm x. Okay, this is actually a positive quantity. This is equal to 0 means the numerator is equal to 0, which means that norm of tx is equal to 0, which implies that tx is equal to 0 for all x is equal to 0. So every element is mapped onto the 0, which is by definition of the 0 transformation, which implies t is equal to 0. So this is the only transformation which maps every element onto 0. So norm t is equal to 0 implies t is equal to 0. And in the other case, if t is equal to 0, then t of x is equal to 0 for all x. T of x is equal to 0 for all x, which means that supremum t of x, supreme x element of d of t x not equal to 0, norm tx by x is always 0, which means that norm t is equal to 0. So concluding both of them together, we can write t is equal to 0 if and only if norm t is equal to 0. Okay, so which implies that the second property holds, n2 holds. Okay, now moving n3, which is norm of alpha t should be written as modulus of alpha into norm t. So which is by definition supremum x element of d of t, norm x equal to 1, norm of alpha tx. So which is by definition supremum x element of d of t, norm x is equal to 1, norm of alpha into tx by definition. So now use the properties of norm. So which is equal to supremum x element of d of t, norm x is equal to 1, modulus of alpha into norm tx, using the property of norm. So which is equal to, if we take the modulus outside, which is equal to modulus of alpha into supremum x element of d of t, x naught norm x is equal to 1, norm of tx. This is actually by definition is actually norm t, so which is equal to modulus of alpha into norm t. So third property is satisfied, that is norm of alpha t is equal to modulus of alpha into norm t. Now moving on to the fourth property, N4, the fourth property. So for the property norm of T1 plus T2, triangle inequality, which we have to prove by the definition supremum x element of D of T, norm x equal to 1, norm of T1 plus T2 of x, which by definition which is equal to T1x plus T2x. So supremum x element of D of T, norm x is equal to 1, norm of T1x plus T2x. Now by the properties of norm, by the triangle inequality, norm of T1x plus T2x is actually less than or equal to norm of T1x plus norm of T2x. So by triangle inequality we can write it as, so this is actually, this quantity is actually less than or equal to supremum x element of D of T, norm x equal to 1, norm of T1x plus, I think I can actually split the supremum as well. Supremum of a plus b is actually supremum of a plus supremum of b, or less than or equal to inequality. So supremum x element of D of T, norm x equal to 1 into norm of T2x. This is actually the definition of norm T1. This is actually the definition of norm T2, which implies, so this is actually equal to norm T1 plus norm T2. Okay, so norm of T1 plus T2 is actually less than or equal to norm T1 plus norm T2. So we have proved all four properties of the norm. So our norm of a bounded linear operator is actually satisfying all the properties of a normed space. So to sum up the whole thing, we were studying about the bounded linear operators. So which is a linear operator which satisfies this condition, and if such an operator exists, there should exist a real number c with which this condition holds. So if this condition holds for a particular c, it holds for every number c which is greater than this c. Okay, so we want the least of such element. That least element is called norm of that operator, and norm of that operator has a two distinct properties. One is actually it has an alternate definition, which is supreme of x element of D of T, norm x is equal to 1, norm of Tx. This is the definition which we are going to use in most of the theorems. The second one is which actually satisfies all the properties of the norm. So this is to prove the first part, we take an element norm x with x not equal to 0 and defining y is equal to 1 by a into x. This is the important part, and use the definition. And to prove the second part, we actually consider the n1, n2, n3, n4 and establish that using the definition of supremum and definition of norm. These four properties are easy to understand. So I hope you understood. Thank you.